Hello everyone and welcome back to another math video. Today we're going to be talking about binomial distribution and normal distribution. This might be one of the last topics of the SL probability unit. So if you have any lingering questions, feel free to either leave them in the comments or send me a message. Today we are going to be going over SL 4.7 and SL 4.8. It's important to keep in mind that while the binomial distribution formulas are in the formula booklet, the normal distribution formulas are not. All right, with all that being said, let's move right on. All right, so we're going to start out here with binomial distribution. So before I start, you'll notice that I am not covering either of the mean or variance formulas from the formula booklet. We can write them out right here if that makes anybody's life a little easier. But the reason why I'm not covering them is because I think they're quite simple. If you are given the number of trials and the probability, then you can multiply them together and get the mean. And then you can multiply the mean by 1 minus the probability to get the variance. The only thing that's really important to keep in mind with this is that variance is going to be the standard deviation squared. So if you need to find the standard deviation, don't forget to take the square root of the variance. All right, moving on. So what is binomial distribution? Binomial distribution is the probability distribution of different repeated outcomes of different binary events. When we talk about binary events, we're exclusively talking about discrete data. So how many leaves are on the plant, or how many cars are in the parking lot. It is discrete data that it does not have a range, it just has a set number, okay? So if we look over here, I have got the formula that's given to us in SL 4.8 that is talking about binomial distribution. So that X in the little squiggly is just denoting that we're talking about distribution, that X is randomly distributed. Moving on. The B is going to stand for the distribution type, which means binary. You'll see later on that we will have an N in that place for normal distribution. Looking right along, N here is going to stand for the number of trials, and P is going to stand for the probability of success. So what do I mean by success? Because not everything is going to have a success or a failure. For example, if we're talking about whether it rains or not, that is a yes or no question, which means that the data is discrete. But there's not really a success or a failure. What I mean by that is if the question is asking you how many days, or what is the probability, or how many days in June, or whatever it's asking, if it's asking you to find how many days there are rain, you are going to want to use the rain as a success and no rain as the failure. Does that make sense? I hope that makes sense. The calculator is automatically going to do any problems that talk about at least. So what I'm talking about here is the difference between PDF and CDF. In our calculator, if we go into our calculator, I'm using the TI 84 Plus Silver Edition. We can do second vars, and then either do 0 to give us binompdf, or second vars alpha A to give us binomcdf. So when we use these two things, they're going to give us different answers. PDF is going to give us one specific situation. So it's asking if you roll a die 3 times, what is the chance of having exactly 2 number 6s? In that case, we would use our total would be, we're rolling it, what did I say, 6 times? 3 times. We're rolling it 3 times, so our total would be 3. Our probability would be 1 over 6. And our ignore this for now, but our number would be, we want exactly 2. That's what we would use in our binomial CDF. Sorry, our binomial PDF. For CDF, these are going to be questions that are asking you to include a range of data. So at least 16 days, or no more than 2 failures. The calculator is automatically going to count for at least. So X is at least 3. Usually when we're talking about word problems, this is going to be what we would consider, that would usually be the phrasing in the question. But we can also think about it in terms of equation where we have x and either this or x and that. In this case, I believe that we are going to be talking about x is at least whatever, right? But if we move on down, the calculator is not automatically going to do no more than. So in order to get no more than, we're going to do 1 minus the binomial CDF. We're still going to put in the total number of trials. We're still going to put in the same probability, but this time we're going to do the number of successes that we want minus 1. So the reason that we're doing it that way is because we want x to be no more than 6. So we want to include all the times 1, 2, 3, 4, and 5 when x is no more than 6. All of those situations are correct. However, if we included 6, then x would be 6, and that doesn't fall in line with the problem. So we cannot use that number. That's why we're doing the minus 1 here. Normally, if we're using binomial CDF, we would not do that minus 1, and we would just use the standard number of successes. I've written something off to the side here as well to keep in mind. Alternatively, and this could be easier if this method hurts your brain. Alternatively, you could do all of the numbers using binomial PDF and then add them all together. So what I mean by that is do the binomial PDF of 1, and then of 2, and then of 3, and then of 4, and then of 5, including 0. Depending on the data, include 0, because that would still be no more than. You could add all of that up, and that would get you, in theory, the same answer. However, if your brain can handle the CDF method, do that method. It's much easier. All right, let's talk about normal distribution. So I realize that we just zoomed right through binomial distribution, but I promise you it's not too difficult. If you have questions, again, feel free to let me know. So normal distribution is when we're going to be wanting to thinking of a bell curve, where most of the data is going to fall in this middle range. Some of it is going to still peter out, and then there's going to be very few on the end. It's always going to deal with continuous data. So what I mean by that is weight or height, or are always two of my favorite examples, because you can have any weight. Technically, we think of weight in that you are either 110 pounds or you're 111. But in reality, you could be 110.27 pounds. And in that way, weight is continuous. So this is always going to deal with continuous data, and that's going to be the difference between binomial and normal. So this little symbol that I keep writing means the mean. That is going to be the very middle of the data. So that's going to be right there. That's going to be the height of our bell curve. 50% of the data is going to lie below, and 50% of the data is going to lie above that point. So if we say that, if given the situation where we need to discuss that, if given a specific number is equal to 0.5, so like probability of x is less than 0.2 equals 0.5, or whatever the case may be. Maybe don't think about it like that. That was a bad explanation. But just keep in mind that half of the data is going to lie above and half is going to lie below. So I have written out here our notation. Again, n meaning normal, u meaning mean. This is going to stand for our standard deviation, and I've added these squared on top of that to denote the fact that it could be given in terms of variance as well. So you might see it written out as x is about, or x squiggle n 2, 0.5 squared. And it could just be written like that on the problem. Just keep in mind that that 0.5 is going to be your standard deviation, and that's what you're going to want to be putting in the calculator, right? So the thing to keep in mind about binomial distribution is because it is continuous, technically our sample space is all real numbers, meaning that you could have something be negative 2,767, or you could have it be 5,000,006 or whatever the case may be. It is all real numbers. It is encompassing every single number that is real, excluding those that are imaginary. And if you don't know what imaginary numbers are, you don't need to. So let's talk about putting this in the calculator. Again, I'm using the TI-84 Plus, but this should remain consistent for other types of calculators as well. So let's start out with this first problem here. We are looking for the probability that A is less than X is less than B. So we would put this in the calculator as a normal CDF. We do also have normal PDFs, but they're just not as common. A, our lower bound. B, our upper bound, then the mean, then the standard deviation. Again, keep in mind we're using standard deviation and not variance. Given this problem here, we're looking at kind of just this part of the question, right? We would put in a negative 10 to the 99th power. So why are we doing this? So we've already discussed the fact that this sample space is going to be all real numbers. So given that the sample space is all real numbers, it can get, you can't start at 0. So the easiest thing to do is just pick a really big negative number. I read this on Cognity, and I agree that negative 10 to the 99th power is going to be the easiest thing to do. Then we're going to put in that upper bound, then again, mean and standard deviation. Finally, we're just looking at this first half of the problem up there, right? Because we can flip it around. And we're again going to do that lower bound, but this time we're going to use 10 to the 99th power as our upper bound because it's just a really big positive number. Then again, mean and standard deviation. Finally, let's talk about the invnorm example, which is just how I'm going to say it because I think it's easier. That's how it's going to appear in your calculator generally. Again, we can get to all these things through the same steps as we did the first time, second vars, and then scroll through to find the one that you want. So I have a problem written out here because I thought this might be the easiest way to go about looking at this, is just to jump right into it. So we have written out here 2.2, 0.5 squared is our mean, and then our standard deviation put in with variance, or denoting that it could also be variance. We are looking for B, so we're looking for B. Given the probability, we are looking for B. So how we're going to put this into the calculator is using this invnorm. We're going to do that probability, then we're going to do our mean, and then we're going to do our standard deviation, okay? And that is going to give us B. As simple as that. So you'll notice here that we have X is less than B. If we have X is greater than B, then we're going to use 1 minus whatever that probability is in place of the original probability, because we always want it to be X is less than B. If we are given a range where we're given one number and not the other, we can use the CDF to find X is less than whatever that lower bound is, then add that to the probability that we were given, and then solve using the invnorm function on our calculator. All right. I hope that was helpful. I hope you've learned something. Please let me know if there are any questions, and I hope this helped.